Hi, let's talk about selection sort algorithm. Selection sort is one of the basic algorithms like insertion sort and bubble sort. It is a comparison based algorithm and has theta n square time in all cases. The good thing about selection sort is it does less memory writes compared to other algorithms. If you compare it with other popular algorithms like quicksort, merge sort, insertion sort, bubble sort, etc., you can notice that this algorithm is going to do less memory writes compared to these algorithms. However, this is not the optimal algorithm in terms of memory writes. There is another algorithm called cycle sort, which is optimal in terms of memory writes. Memory write can be a costly operation in situations like EEPROM. In EEPROM, if we do more writes, age of this memory reduces. So in those cases, we can prefer selection sort over other sorting algorithms. It's a basic simple sorting algorithm and can reduce memory writes. Not only EEPROM, there can be other situations where memory writes are costly. Suppose you are writing data to hard disk. You are sorting some files and you are putting individual files on the hard disk when you are swapping them or when you are putting them into the memory. So this is an advantage of selection sort. Next important point about selection sort is it's a basic idea for heap sort. Heap sort idea is based on selection sort only. It is just that heap sort uses heap data structure to optimize the selection sort idea. Selection sort is not stable in basic form. When we do selection sort, the order of equal elements may change. The next point is it's an in-place algorithm. It does not require extra memory for sorting. Let us now understand the basic idea of selection sort algorithm. With this example, we are going to sort this array in increasing order. So the basic idea of selection sort algorithm is we find out the minimum element, we put it at the first position. Then we find out the second minimum element and put it at the second position. Then we find out the third minimum element and put it at the third position. We keep doing it. At the end, we have the array sorted. Now please pause this video and try to implement this idea. Let us see the naive implementation now. We first traverse the input array, find out the minimum element and put it at the first position in our temp array, and we replace this element with infinite. Now we traverse through the input array again, find out the minimum element again and put it at the next position in temporary array and replace this element with infinite. Now we traverse through the input array again, find out the minimum element, put it here and replace it with infinite. Same thing we do for remaining elements. This is replaced with infinite, comes here, replaced with infinite and comes here, replaced with infinite and comes here. That's how we get the sorted array. Let's see the implementation. We have created a temporary array of same size. Now we are traversing through the input array. This I decides the index where this next minimum has to be put. So first time index I was 0, so we put 2 at index 0. And inside this loop, we find out the minimum element first. Right? We initialize the index of minimum element as 0. Then we traverse through elements from 1 to n-1. And we compare it with the current minimum. If it's smaller than current minimum, then you update the current minimum. And after that, we put the found minimum element at index I and we put the value infinite at this minimum element index. And at the end, we copy the temporary array back to the original array so that our original array is modified and we have the sorted array. So we are going to copy these elements here. 2, 5, 8, 10, 18 and 20. So this is our final sorted array. Now please pause this video and try to optimize this solution. In this solution, we are using an extra array temp, right? And this selection sort algorithm should be in place. We should not be using extra array to store the sorted array. Let us now see a better implementation that does not use an auxiliary array. We do all operations within the same array. Let's now understand the idea with this example. In the first iteration, like the naive implementation, we find out the minimum element, which is 2 here. And instead of putting this 2 into a temporary array, we know this 2 is going to be at index 0. So we swap it with the current element at index 0. So 10 comes here, the current element at index 0 comes here, and this element goes to the index 0, right? And now what we do is, we know this element is sorted. This is fixed at its correct position. Now we have this remaining array, and we find out the minimum element in this remaining array. And minimum element in this remaining array is 5. And next position where this minimum element should go is also 5. So we swap 5 with 5 and we have this array now. So these two elements are sorted. Now we again find out the minimum element in the remaining array. And minimum element in the remaining array is 8. And the position where it should be is also the third position. So we swap 8 with 8 itself and we have this part sorted. Now we find out minimum element in the remaining array. Please note that at every point we are maintaining two arrays. One array which is already sorted and one sub-array which is yet to be sorted. And we find out the minimum element in the unsorted part. So minimum element now is 10. And where 10 should go now? It should go at this position. So we swap these two elements. So 10 comes here and 20 goes there. Now we have remaining unsorted array as these two elements. We find out the minimum among these two, which is 18, and we swap it with the position, with its original position. So they are swapped. So we have 18 here now. Now we have only one element remaining. We find out the minimum element in this one element, which is 20 itself, and we swap 20 with 20. We can in fact skip the last execution part of this code or this algorithm, because we know it's going to be only one element and there's no point swapping this element with itself. We can actually optimize this to run to n-1 instead of n, right? This is one optimization we can make because this part is not necessary. There's only one element left and it's going to be swapped with itself only. So let's now see the implementation. We are running a loop for I equal to 0 to n-1, where elements from 0 to I are maintained to be sorted and elements from I plus 1 to n-1 are not yet sorted. So we find out the minimum element from the unsorted part from I plus 1 to n-1. We find out the minimum element, we find out the index of the minimum element in a variable called min index. And once we have found the minimum element, we swap it with the array I, because we know this element should be going at the array I, and we move the element minimum index to I and I to minimum index. We swap these two, right? That's the simple implementation of this selection sort. Let's now see stability in selection sort algorithm. Selection sort is not called stable because if there are two elements with the same value, it may change the order of these elements. And why do we care about stability? See, these two items values which are there in the arrays, they might represent individual values of the objects. For example, these values are marks of the students and these students are ordered according to maybe alphabetically or institute name. And if there are two students with the same marks, we want to keep them in alphabetic order, right? We don't want to change that order. So if we apply selection sort here, what happens here is this 90 moves to a position after this 90. See, in the first iteration, what we do in this selection sort, we find out the index of minimum element, which is 3, and we swap it with the first element. So this 90 comes here, and that's where this selection sort becomes unstable, right? And rest of the algorithm follows the same process, right? But this is the step where we have instability, and these 90s never change their position back again because it has come to the end, its final position. So we do not have stability in selection sort. Let us now see the time complexity of selection sort. So the innermost statement is this statement that executes maximum number of times. Let's now try to find out how many times this is going to execute. When I is 0, it's going to execute n-1 times. This condition is going to be checked n-1 times. When I is 1, it's going to be checked n-2 times. And when I reaches n-2, it's going to be checked 1 times only. So this condition is being checked these many times. In the first iteration of I, it's going to check n-1 time, then n-2 times, n-3, and so on, then 2 and then 1. If we sum this series, we are going to get n into n-1 by 2, which is theta n square. So this particular statement is being executed theta n square time, and this is the most executing statement of this loop, of this code. So that's why the time complexity of selection sort is theta n square. And in selection sort, it does not happen that there is a best case which is having time complexity less than n square. It always takes n square time. Even if you provide the sorted array, it's going to take n square. Even if you provide reverse sorted, then also it's going to take n square.